Yeah. Change in density with respect to change in temperature. Just use the typical difference quotient. So what I could use for these numbers, I could take 24.93, that's a density at the specific spot, and subtract 24.62. So .93, 24.62 divided by, and then I'm going to take a look at the difference in temperatures. So temperature 8 minus temperature 10. Make sure you do it in the same order. That would be one estimate, or you could take a look at these two. So you could take your 24.93, subtract from it 25.22, and divide that by the different values for the temperature corresponding to those two numbers, and you want to make sure you do it in the order in which you subtracted up above. Or you could just take the average. See how this goes. Sometimes people will say, can you just go 24.62 minus 25.22 and straddle the point? And not probably a good idea, primarily because you want to actually incorporate what you're after, that particular point. And if you straddle the point, you're not actually including that point in your computation here. So, you know, probably the best thing to do is to do both of these and take the average. This would be if you really were trying to get these numbers out. On an exam, because this is a likely type of test question, just one is sufficient. Okay. All right. Any questions here? Okay. You get similar problems. Oh, I guess I should back up. If I was looking for this, but now, not volume, what is it? Temperature. Okay, if I was looking for this, then I would be picking out this same point, 24.93, but here I'm going to hold temperature constant, and instead we'll be varying salinity. And so I will be looking at neighboring points to the left and the right. So that you literally get that feeling of partial derivatives measuring rates of change as you come into a point either vertically, up and down, or horizontally, left and right. You guys see what I'm saying there? So you get that nice feel from this. this particular set of data is sitting in table 1, page 804 of the text. The graphical aspect of this, well, if we were looking at the rate of change of a function f with respect to x, and we are looking at it at this point q, we would be taking a look at picking up neighboring values of f from the level curve minus the appropriate changes in x, which this is kind of a pain down here because you can't, they don't even give you a scale in x. So I don't know how they expect you to do that without actually having your scale in x. It's kind of nasty. But it's that same idea of vertical versus horizontal changes. Do you see that, Tony?
Well, if you assume the same scale,
but that's
I think you're supposed to, whatever scale they want to impose for x and y, I think you're just supposed to measure the distance between the level curves as their, is the greater distance here.
How do I know that the scales are the same?
Since it's not told, I would just assume that they are.
Yeah,
what assuming does. But
a better problem, I guess, would be
the graph on 54 has the scale there,
That's the one that's going to probably, I don't know if the new book is going to make these corrections. I mean, it drives me nuts in this book that they start doing things like seawater density, but they don't even begin to tell you what the units are. How useless is data if you don't even know what they're measuring with? But, and they consistently do that in a number of places. But that notwithstanding. Okay, so that gives you numerical fields for this data. The other thing which I want to mention are differential equations. So some of you guys have taken the differential equations class, is that right? Some of you have, and if you haven't, you've seen differential equations in Calc3, I think. There's a little mini chapter. So,
here's Indian.
Oh, thanks. So when you look at ordinary differential equations, you might see something like, I don't know, y double prime plus 3y prime minus 4y equals 0. And the goal here is to find functions y, a function of one variable that satisfies this equation. Okay, that's what it means to be a solution. So, same stuff. When you first do algebra, before you start solving equations like this, you get asked questions like, is x equals 1 a solution? How do you tell? You plug x equals 1 in and see if you get back a valid statement. And it's the same deal here. I can ask you, is y equals e to the 4x a solution? And what you would do, or did do, second derivative of e to the 4x, well, the first derivative is 4e to the 4x, so second derivative is 16e to the 4x. First derivative, kind of doing this backwards, 4e to the 4x, and you plug these guys in and see, do you get a valid statement? So plug it in and ask, is this the case? And the answer here is no, so it's not a solution. On the other hand, you can check this is a solution. So I'll leave it to you to verify that. Okay? This is an example of what is typically called an ordinary differential equation. Function is a function of one variable. The derivatives are just regular Calc 1 type of derivatives. You've got a function of one variable. So, there's partial differential equations. So suppose we have a function u, and we're looking for solutions to partial of u with respect to t is equal to the second partial of u with respect to x twice. Okay? So what we want to do here, so this is problem, where is this? This is exercise 76 on page 804, is you want to verify that u of xt equals sine of nx e to the minus n squared t solves this equation. Okay? I can remember loads of partial differential equations in thermodynamics classes that I took. I was a chemistry major. They were all over the place. Okay? This particular equation is called the heat equation. It's being stated here where t is time, x is position, but it generalizes to 2 and 3 dimensions relative to the position. Okay? So you get these equations floating around. They're not going to ask you to solve them, but what they're going to do is either say verify that something is a solution or simply ask you, is this a solution? There are a bunch of these problems in the book there at the end of the chapter in 14.4. So differentiate with respect to t. Differentiate twice with respect to x. And see if they work out the same. So, revise. your deal. Give you good practice on our derivatives. You guys are so quiet tonight. See, they're having fun. If he starts showing a movie, I'm out of here.
Is that George Spatar next door?
I get all those people
Don't know.
mixed up.
Oh.
Yeah. So I'm done. You guys done? Take a look. You haven't quite finished. Here's the U. Differentiate with respect to t. There's no t in this sine term, in the sine part. So I just have to differentiate e to the minus n squared t, and derivative of e to the minus n squared t. I just copy that down and differentiate the exponent. There's my minus n squared. Differentiating u with respect to x, all I worry about is the sine of nx part. So that derivative and cosine of nx, and then there's the e. Do it again, I'm going to get another n out front, and it's a minus. Derivative of cosine gives you minus sine. So we have this, and then I'm just looking, is this the same as that? And the answer is yes. So it's a solution. Okay. Questions here? These problems are hell if you don't know how to differentiate. make sure you know how to differentiate. So remember, first day I was saying, list in the book, you know, you're expected to know derivatives of your trig functions, exponentials, logarithms, inverse sine, inverse tangent. Okay, and then the various rules. Okay, guys. That's it on 14.5. Let me get started a little bit. I'm sorry, that's it on 14.3. Let me get started a little bit on 14.4. I'm not going to do this real rigorously. But let me first of all talk about differentials in one variable. Okay. F of x is x squared. What's the difference between the following? No, they're not the same.
Isn't in respect to x?
Yeah, it is. I just have a function of one variable.
One's a partial derivative.
No, this is Calc 1, pretend. Except for when you see this stuff in Calc 1, it's still probably in the middle of everything else. Maybe too much at the time, and you don't quite pick up the difference. Let's suppose this is giving me position in centimeters at, well, okay, let me see. Usually in Calc 1 you do S of t. So let me do this and tell you that this is a function that will give me position measured in centimeters at time t, which is in seconds, and then I'm going to ask for the difference between derivative of s with respect to time, or s prime of t, and this. So s prime is velocity. I can compute it easily. It's 2t, and the units would be centimeters, position units in the numerator, time units in the bottom, centimeters per second. Okay? What's this? The units of this are centimeters. They're S units. How do we compute it? Well, you Calc 2 people. Didn't you compute these? Every time you do an integral? except people tend to be somewhat sloppy with notation. So in this case, ds is 2t dt. Now, what do these things represent? You give me a small change in time, and this is going to measure a small change in position, which would be at the distance that you travel. Okay? Think about it like this. If you think about velocity as being the change in position over change in time, so that's how that's kind of the high school version of what velocity is. The other way to look at this is that change in position is equal to the velocity times the change in time. This all holds when your velocity is constant, which is not the case up above, but I do want you to see the relationship between this and this. Their change in position, that's a velocity. That's a change in time. But this is a slightly different situation because this is assuming constant velocity. This is not. This is measuring the dt small changes in your time. Small changes. If your velocity is constant, I can say I'm traveling 70 miles an hour down the road. I can say how far will I have traveled in 10 hours, in 5 hours. It doesn't matter because my velocity is constant. This formula is going to hold. But if I don't have a constant velocity, I can't just randomly do this. But what I can do is to apply this when I am talking about very small changes in time. And that will then give rise to small changes in position. Okay? You do this, for instance, if you integrate v of t, velocity, dt, which is what this is, s prime of t dt. Fundamental theorem of calculus says s of b, position at time b minus position at time a. Well, where is it coming from? It's coming from multiplying velocity times time. Now, it's actually doing that by dividing that time segment up into little tiny intervals of time. And then pretending that although velocity isn't constant, I pretend it's constant on each subinterval. And then you divide up finer and finer, and in the end, you take the limit as you do these partitions finer and finer, and you end up with this. Okay? So, what I'm looking at with a differential function in one variable is something a little bit more specific than this guy. I'm looking at this as small changes. Sometimes people will talk about them as being errors. You know, if I'm off by 0.01 millimeters when I manufacture a ball bearing, how far off will the volume of that bearing be? That's a differential. The differential of the radius, say, 0.01 millimeters, and then compute what the corresponding change in volume would be when I'm off by that amount. You guys see what I'm saying? Well, we've got the same problem with functions of more than one variable. So if I said that I have a function f of xy, and actually let's make this xt. Actually, let me change letters. T x little t. So this is going to give me temperature, which I'd measure, say, in Kelvin of the ground at a depth of, say, x centimeters at time t. So say we look at this in terms of seconds, not seconds, probably minutes, it'd be more realistic. Okay, so you have the ground at a particular time of day. If you go looking at the partial of t with respect to x, this is fixing a time of day and then measuring what is the rate of change of the temperature as you start going underground. And that's going to change at first, but after you go sufficiently far, it's probably going to be constant. Although you keep going farther down and it starts heating up. That's what this would be measuring, changes in temperature with respect to depth. On the other hand, if you look at this, you're fixing a depth, maybe 5 centimeters under the ground, maybe right at the ground level. And you're concerned with how temperature is changing at that depth over the course of a day as time changes. If you dig far enough down, if your depth is pretty far under, this rate of change is probably pretty close to 0. But up near the surface, if you're seeing like a day like today, on the surface, this temperature change, it's going to change a lot. And so you'll get a fairly big rate of change. Okay? These are the derivatives, they're rates of change. But now what I'd like to know is